Question 1. The review process indicates a potential misunderstanding in the object-oriented design of a pet management system. Specifically, the team is debating how to model the relationship between different types of pets. Considering the is-a relationship as the primary criterion for inheritance, which of the following approaches best reflects sound object-oriented principles and professional best practices for a Java SE application? Option A. A dog class extends an animal class. Option B. A car class extends an animal class. Option C. A dog class extends a vehicle class. Option D. A cat class extends a dog class. Correct answer is A. A dog class extends an animal class. Explanation. The review process indicates a need to ensure that the inheritance hierarchy in a Java application accurately reflects real-world relationships and adheres to best practices for maintainability and extensibility. This scenario is professionally challenging because a poorly designed inheritance structure can lead to significant technical debt, making the code difficult to understand, modify, and debug. Developers must exercise careful judgment to ensure that the is-a relationship is correctly implemented, avoiding situations where a subclass is not truly a specialized form of its superclass. The correct approach involves designing the inheritance hierarchy such that a dog class extends an animal class. This is because a dog is a specific type of animal, embodying the is-a relationship. This approach promotes code reusability, as common behaviors and attributes of animals can be defined in the animal superclass and inherited by dog. From a professional and ethical standpoint, this aligns with the principle of clear and accurate representation of domain concepts, which is crucial for building robust and trustworthy software. It also facilitates easier testing and maintenance, as changes to common animal behaviors only need to be made in one place. An incorrect approach would be to have a car class extend an animal class. This violates the fundamental is-a relationship. A car is not a type of animal, and forcing this inheritance would lead to a nonsensical and unmaintainable code structure. This represents a failure in professional judgment and a disregard for the principles of object-oriented design, potentially leading to incorrect program behavior and significant future development costs. Another incorrect approach would be to have a dog class extend a vehicle class. Similar to the previous example, this breaks the is-a relationship. While both dogs and vehicles can move, a dog is not a type of vehicle. This misrepresentation of the domain model is a professional failing that compromises code integrity and clarity. It would also likely lead to the introduction of irrelevant methods and properties in the dog class, further complicating its usage and maintenance. A final incorrect approach would be to have a cat class extend a dog class. While both are animals, a cat is not a specialized type of dog. This also misrepresents the is-a relationship. It would imply that all characteristics of a dog are applicable to a cat, which is false, and would necessitate overriding many inherited methods, negating the benefits of inheritance and leading to a less maintainable design. This demonstrates a lack of understanding of how to properly model relationships through inheritance. Professionals should employ a decision-making framework that prioritizes understanding the core nature of the objects being modeled. Before implementing inheritance, ask, is object A truly a specialized form of object B? If the answer is yes, inheritance is likely appropriate. If the answer is no, consider alternative design patterns like composition or interfaces. This rigorous application of conceptual understanding ensures that the resulting code is not only functional, but also maintainable, understandable, and ethically sound in its representation of the problem domain. Question 2. What factors determine the most appropriate conditional statement structure for implementing user access control to sensitive financial data within a Java application, considering the need for both security and clarity? Option A. The requirement to match a single variable against a set of predefined constant values to determine a specific action. Option B. The need to evaluate a series of distinct, ordered conditions and subconditions to grant or deny access, ensuring a clear audit trail and adherence to security policies. Option C. The desire to execute a block of code if a single, broad condition is met, without considering further granular checks. Option D. The goal of executing multiple independent checks where the order of evaluation does not significantly impact the final outcome. The correct answer is B. The need to evaluate a series of distinct, ordered conditions and subconditions to grant or deny access, ensuring a clear audit trail and adherence to security policies. Explanation. This scenario presents a professional challenge because a programmer is tasked with implementing logic that directly impacts user access to sensitive financial data. The ethical dilemma arises from the potential for a flawed implementation to lead to unauthorized access or denial of legitimate access, both of which have significant legal and reputational consequences. The programmer must balance the need for efficient code with the absolute requirement for security and adherence to data privacy regulations. Careful judgment is required to ensure that the conditional logic is robust, unambiguous, and correctly reflects the intended access control policies. The correct approach involves using nested if-else statements to create a clear, hierarchical decision-making process for access control. This approach is right because it allows for the precise evaluation of multiple conditions in a specific order, mirroring the complexity of real-world access rules. For example, a user might first need to be authenticated, then checked for role-based permissions, and finally, for specific data segment access. This structured evaluation ensures that each condition is checked sequentially, and the program only proceeds to the next level of scrutiny if the preceding conditions are met. This aligns with the principle of least privilege and robust security practices, which are implicitly mandated by general data protection and financial regulation frameworks that require secure handling of sensitive information. The explicit, step-by-step nature of nested if-else statements makes the logic auditable and easier to verify against security policies, thereby reducing the risk of unintended access. An incorrect approach that relies solely on a series of independent, if statements without proper chaining or nesting would fail to enforce the intended hierarchy of checks. This could lead to a situation where a user who should be denied access at an earlier stage might still gain access if a later, less restrictive condition is met. This violates the principle of layered security and creates significant vulnerabilities. Another incorrect approach using a switch case statement for this scenario would be inappropriate. Switch case is designed for evaluating a single variable against multiple discrete, constant values. It is not suited for evaluating complex, compound conditions or ranges of values, which are typical in access control logic. Attempting to force complex conditions into a switch case structure would result in convoluted, unreadable, and error-prone code, failing to meet the clarity and maintainability standards expected for security-sensitive code. This lack of clarity makes it difficult to ensure compliance with regulatory requirements for data protection and access control. A third incorrect approach might involve overly simplistic conditional logic that doesn't account for all edge cases or potential security loopholes. For instance, assuming all users within a certain broad category have access without further granular checks would be a critical failure. This demonstrates a lack of due diligence in understanding and implementing the full scope of access control requirements, potentially leading to breaches of data privacy regulations that mandate specific controls for sensitive information. The professional decision-making process for similar situations should involve 1. Thoroughly understanding the business requirements and the specific data access policies. 2. Identifying all relevant conditions and their hierarchical relationships. 3. Selecting the control flow structure, if-else, nested if-else, that best represents these relationships and ensures clarity and auditability. 4. Rigorously testing the implementation against all defined scenarios, including edge cases and potential attack vectors. 5. Seeking peer review for security-critical code. Question 3. The assessment process reveals a Java application that frequently manipulates user-provided text data. A developer is tasked with optimizing a section of code that involves repeatedly appending text to an existing string within a loop. The developer considers several strategies to achieve this efficiently and correctly, keeping in mind the fundamental nature of string handling in Java. Option A. Continuously reassign the original string variable with the result of the plus concatenation operator within the loop, as this is a straightforward way to build the final string. Option B. Utilize the string concat method repeatedly within the loop, assigning the result back to the original string variable. Option C. Create a new string object in each iteration of the loop by calling the string constructor with the accumulating string and the new text. Option D. Use the string builder class to append text within the loop, as it is designed for mutable string operations and avoids the creation of numerous intermediate string objects. The correct answer is D. Use the string builder class to append text within the loop, as it is designed for mutable string operations and avoids the creation of numerous intermediate string objects. Explanation. The assessment process reveals a common scenario in Java development where understanding string immutability is crucial for efficient and secure code, particularly in environments where data integrity and resource management are paramount. The challenge lies in recognizing how string operations can inadvertently lead to the creation of numerous temporary string objects, impacting performance and memory usage. Professionals must discern between operations that modify strings in place, which is not possible with Java's string class, and those that create new string objects. This requires a deep understanding of the Java memory model and the string pool. The correct approach involves leveraging string manipulation methods that are designed to be efficient and minimize object creation, or understanding when to use mutable string alternatives like string builder or string buffer when frequent modifications are necessary. This aligns with professional best practices by promoting code that is both performant and resource conscious. Ethically, it ensures that the software delivered is robust and reliable, meeting client expectations for quality and efficiency. An incorrect approach involves repeatedly concatenating strings using the plus operator within a loop. This is professionally unacceptable because each concatenation operation creates a new string object, leading to significant overhead in terms of object creation and garbage collection. This can degrade application performance and increase memory consumption, potentially leading to out-of-memory errors in long-running applications. From a regulatory perspective, while not directly violating specific Java SE programmer exam regulations, delivering inefficient code can be seen as a failure to adhere to professional standards of quality and competence expected of certified professionals. Another incorrect approach is to assume that methods like replace or substring modify the original string object. These methods, like most string methods in Java, return a new string object with the modifications. Continuing to use the original, unmodified string object when the intention was to work with the modified version leads to logical errors and unexpected behavior, undermining the reliability of the application. This represents a failure in understanding fundamental Java string behavior, which is a core competency for the OCP Java SE Programmer certification. The professional reasoning process for similar situations should involve 1. Identifying the core operation. Determine if the operation requires modification of string data. 2. Evaluating string immutability. Recall that Java's string objects are immutable. 3. Assessing performance implications. Consider the potential for object creation and garbage collection overhead with repeated string operations. 4. Choosing the appropriate tool. Select between string builder, or string buffer based on the frequency and nature of string modifications. 5. Testing and profiling. Verify the performance and correctness of the chosen approach. Question 4. The audit findings indicate that a data processing loop designed to iterate through a list of transaction records is exhibiting unexpected behavior. Specifically, when a transaction record has an invalid status code, the loop should skip processing that particular record and move on to the next one, but it should not terminate the entire processing sequence. The current implementation needs to be reviewed to ensure it correctly handles these invalid status codes according to the established data integrity guidelines. Option A. Use the continue statement to skip the current iteration when an invalid status code is detected. Option B. Use the break statement to exit the loop entirely when an invalid status code is detected. Option C. Remove the conditional check for the status code and process all records regardless of their validity. Option D. Implement a Boolean flag variable to manually control whether the loop proceeds to the next iteration. The correct answer is A. Use the continue statement to skip the current iteration when an invalid status code is detected. Explanation. Scenario analysis. This scenario presents a common challenge in software development where the efficient and correct implementation of loop control mechanisms is critical for maintaining data integrity and adhering to processing requirements. The audit findings highlight a potential deviation from expected behavior, which could lead to incorrect data processing or system inefficiencies. The professional challenge lies in accurately identifying the intended logic and selecting the loop control statement that precisely matches that intent, ensuring compliance with established coding standards and the overall system design. Misapplication of break or continue can have cascading effects on downstream processes, making careful judgment paramount. Correct approach analysis. The correct approach involves using the continue statement. This is because the requirement is to skip the current iteration of the loop when a specific condition, an invalid status code, is met, but to allow the loop to proceed with subsequent iterations. The continue statement achieves this by immediately transferring control to the next iteration of the loop, effectively skipping the rest of the code within the current iteration. This aligns with the principle of least surprise and ensures that only valid data is processed, maintaining data integrity as per typical regulatory expectations for data handling systems. Incorrect approaches analysis. Using the break statement is incorrect because it would terminate the entire loop prematurely when an invalid status code is encountered. This would prevent the processing of any subsequent valid records, leading to incomplete data processing and potential data loss, which is a significant regulatory failure in systems handling sensitive information. Employing a flag variable to manually control loop progression without using break or continue, while functional, is less direct and can make the code harder to read and maintain. While not a direct regulatory violation in itself, it deviates from standard, idiomatic Java practices for loop control, potentially increasing the risk of future errors during maintenance, which indirectly impacts compliance with maintainability standards. Relying solely on an if statement without any loop control statement would mean that the code inside the if block, which would presumably handle the invalid status, would execute, but the loop would continue to the next iteration regardless. If the intent is to skip processing for invalid items, this approach, without a continue, would still execute subsequent code within the loop for the invalid item, which is not the desired behavior of skipping. Professional reasoning. Professionals should approach such situations by first thoroughly understanding the business or system requirement for handling specific conditions within a loop. This involves clarifying the desired outcome. Should the loop stop entirely, or should it simply skip the current item and proceed? Once the requirement is clear, the developer should select the loop control statement break or continue that most directly and clearly implements that requirement. Adhering to established coding conventions and best practices for loop control enhances code readability, maintainability, and reduces the likelihood of introducing bugs, which are foundational to professional software development and indirectly support regulatory compliance by ensuring system reliability. Question 5. System analysis indicates that a Java application requires frequent manipulation of string data within a method that is guaranteed to be executed by only a single thread at any given time. The primary performance metric for this operation is the speed of string concatenation and modification, which approach best adheres to professional Java development practices for this specific scenario. Option A. Use string concatenation with the plus operator for all string manipulations. Option B. Use string builder for all string manipulations. Option C. Use string builder and implement external synchronization mechanisms. Option D. Use string buffer for all string manipulations. The correct answer is B. Use string builder for all string manipulations. Explanation. This scenario presents a common challenge in software development where performance and thread safety are critical considerations. The professional challenge lies in selecting the appropriate mutable string manipulation tool based on the specific operational context, balancing efficiency with the potential for concurrent access issues. Misjudgment can lead to subtle bugs, performance degradation, or even data corruption in multi-threaded environments, impacting the reliability and integrity of the application. The correct approach involves utilizing string builder for single-threaded operations due to its superior performance. This is justified because string builder is not synchronized, meaning it avoids the overhead associated with locking mechanisms. In a single-threaded context, there is no risk of concurrent modification, making the lack of synchronization a performance advantage. This aligns with the principle of using the most efficient tool for the job when thread safety is not a concern, a fundamental aspect of professional Java development focused on optimizing resource utilization. An incorrect approach would be to use string buffer for single-threaded operations. This is professionally suboptimal because string buffer's synchronization overhead is unnecessary in a single-threaded environment. While it guarantees thread safety, this safety comes at the cost of performance, making it less efficient than string builder when concurrency is not a factor. This represents a failure to apply the principle of least privilege and unnecessary complexity, leading to reduced application responsiveness. Another incorrect approach is to use string builder in a multi-threaded environment without external synchronization. This is a critical regulatory and ethical failure. String builder is not thread safe, meaning multiple threads attempting to modify the same string builder instance concurrently can lead to unpredictable results, data corruption, and race conditions. This violates the implicit professional obligation to produce robust and reliable software, potentially leading to system instability and data integrity breaches, which could have significant downstream consequences. The professional decision-making process for similar situations should involve a thorough analysis of the execution context. First, determine if the string manipulation will occur in a single-threaded or multi-threaded environment. If single-threaded, prioritize string builder for performance. If multi-threaded, evaluate whether the string builder instance will be shared across threads. If shared, external synchronization mechanisms, like synchronized blocks or concurrent data structures, must be employed to ensure thread safety, or string buffer should be used if its built-in synchronization is sufficient and acceptable for the performance profile. This systematic evaluation ensures that the chosen tool aligns with the application's concurrency requirements and performance goals, upholding professional standards of quality and reliability. Question 6. Stakeholder feedback indicates that the current Java application's handling of financial transaction amounts is leading to occasional inconsistencies. Developers are reviewing the code to ensure accurate representation and manipulation of these monetary values. Consider a scenario where a system needs to store and perform arithmetic operations on whole dollar amounts. Which of the following approaches best adheres to the principles of efficient and accurate data handling in Java for this specific requirement? Option A. Declare variables for monetary amounts as primitive int types. Option B. Declare variables for monetary amounts as string types. Option C. Declare variables for monetary amounts as float types. Option D. Declare variables for monetary amounts as integer wrapper objects. The correct answer is A. Declare variables for monetary amounts as primitive int types. Explanation. This scenario is professionally challenging because it requires developers to accurately represent and manipulate different types of data within a Java application, directly impacting the integrity and correctness of financial calculations and reporting. Misunderstanding the nuances between primitive and reference types can lead to subtle but critical bugs, potentially resulting in financial discrepancies or incorrect system behavior. The Oracle Certified Professional Java SE Programmer certification emphasizes a deep understanding of these fundamental concepts, as they are the building blocks for robust and reliable Java applications. The correct approach involves using primitive int for whole numbers representing monetary values, ensuring precise arithmetic operations without the overhead or potential for null pointer exception associated with object wrappers unless explicitly needed for specific Java math functionalities. This aligns with best practices for performance and predictability in numerical computations. An incorrect approach that uses integer objects for all monetary values, while seemingly object-oriented, introduces unnecessary overhead and the risk of null pointer exception if not meticulously handled. This can lead to unexpected runtime errors and reduced performance, which are unacceptable in a professional financial application. Another incorrect approach that attempts to store monetary values as string objects is fundamentally flawed. Strings are designed for textual representation, not numerical computation. Performing arithmetic operations on strings requires explicit parsing and conversion, which is inefficient and error-prone. This violates the principle of using the most appropriate data type for the intended purpose, leading to potential data corruption and incorrect calculations. The professional decision-making process for such situations should involve 1. Understanding the core requirements. Clearly define what data needs to be stored and how it will be used. 2. Evaluating data type suitability. For numerical data, prioritize primitive types for performance and predictability unless object-oriented features or specific Java math functionalities are required. 3. Considering potential pitfalls. Be aware of common issues like null pointer exception with reference types and the inefficiencies of using strings for numerical operations. 4. Adhering to best practices. Follow established Java programming conventions for data representation and manipulation to ensure code clarity, maintainability, and correctness. Question 7. The audit findings indicate a potential vulnerability in the customer class, which stores sensitive financial information. The current implementation declares account number and credit score as public instance variables and provides no specific methods for their controlled modification, Which of the following class definitions best mitigates the identified risk and aligns with secure coding practices for handling sensitive data? Option A. Declare account number and credit score as private instance variables and make all getter and setter methods private. Option B. Declare account number and credit score as protected instance variables and provide public getter and setter methods. Option C. Declare account number and credit score as public instance variables and remove all methods related to them. Option D. Declare account number and credit score as private instance variables and provide public get account number, set account number string, get credit score, and set credit score, int methods. The correct answer is D. Declare account number and credit score as private instance variables and provide public get account number, set account number string, get credit score, and set credit score, int methods. Explanation. The audit findings indicate a potential risk in how sensitive customer data is being handled within the Java application. This scenario is professionally challenging because it requires developers to balance the need for functional code with stringent data privacy regulations. Misinterpreting or overlooking class definition, best practices can lead to security vulnerabilities and noncompliance, resulting in significant legal and financial repercussions. Careful judgment is required to ensure that class members are declared with appropriate access modifiers, aligning with the principle of least privilege and data encapsulation. The correct approach involves defining the customer class with private instance variables for sensitive data like account number and credit score. Methods to access and modify this data should be public getter and setter methods. This adheres to the principle of encapsulation, a core tenet of object-oriented programming, and a fundamental requirement for data protection under relevant privacy laws. Encapsulation restricts direct access to sensitive data, allowing controlled modification through defined interfaces, getters and setters. This controlled access is crucial for auditing, logging, and enforcing business rules, thereby minimizing the risk of unauthorized data exposure or manipulation. This approach directly supports regulatory compliance by ensuring data integrity and confidentiality. An incorrect approach would be to declare instance variables like account number and credit score as public. This exposes the sensitive data directly to any part of the application that can access the customer object, bypassing any intended control mechanisms. This violates the principle of encapsulation and creates a significant security risk, making it difficult to track data access and modifications, and directly contravening data protection regulations that mandate secure handling of personal information. Another incorrect approach would be to declare all methods, including those that modify sensitive data, as private. Private methods are essential for internal implementation details. Making all data modification methods private would render the class unusable for its intended purpose, as external code would be unable to update customer information. This is not a security measure, but a functional failure. A third incorrect approach would be to use protected access modifiers for sensitive instance variables. Protected members are accessible within the class, subclasses, and classes in the same package. While more restrictive than public, it still allows broader access than private, potentially exposing sensitive data to unintended recipients within the package or through inheritance, which is not ideal for highly sensitive information and can lead to compliance issues. Professionals should employ a risk-based decision-making framework. This involves first identifying sensitive data elements. Then, for each element, determine the minimum level of access required for its functionality. Apply the principle of least privilege by using the most restrictive access modifier, typically private, for instance variables holding sensitive data. Define public getter and setter methods to provide controlled access and modification capabilities. Regularly review class definitions and access control mechanisms to ensure ongoing compliance with evolving regulatory requirements and security best practices. Question 8. Risk assessment procedures indicate that the development of a new financial transaction processing module requires a robust and secure object-oriented design. The module must ensure data integrity, prevent unauthorized access to sensitive information, and be easily maintainable for future regulatory audits. Considering these requirements, which of the following approaches best aligns with the principles of object-oriented programming to meet these objectives? Option A. Design classes with minimal use of private members, exposing most data and methods directly to facilitate easy access and modification by other parts of the system. Option B. Implement classes using private fields and public methods, getters and setters, to control access to internal state, utilize inheritance for code reuse where appropriate, and employ polymorphism to allow for flexible handling of different transaction types. Option C. Rely heavily on static methods and global variables to manage transaction state, minimizing the need for object instantiation and interobject communication. Option D. Create a large, monolithic class that handles all transaction logic to simplify the overall structure and avoid the complexities of multiple interacting objects. The correct answer is A. Design classes with minimal use of private members, exposing most data and methods directly to facilitate easy access and modification by other parts of the system. Explanation. This scenario presents a professional challenge because it requires a Java developer to balance the technical implementation of object-oriented programming, OOP, principles with the need for clear, maintainable, and secure code, which indirectly impacts compliance with general software development best practices that underpin regulatory adherence. The core of the challenge lies in choosing an OOP design that best models the business domain, while minimizing potential vulnerabilities and facilitating future audits or modifications, which are often implicitly required by regulatory frameworks governing software quality and security. The correct approach involves leveraging encapsulation to protect internal data and behavior, inheritance to promote code reuse and establish clear relationships between classes, and polymorphism to allow for flexible and extensible code. This aligns with best practices for building robust and maintainable software, which is a foundational element for meeting broader regulatory expectations regarding software integrity and reliability. By encapsulating data, the system reduces the attack surface and prevents unauthorized modification, a key aspect of data protection regulations. Inheritance and polymorphism contribute to a well-structured codebase that is easier to understand, test, and audit, thereby supporting compliance with standards that require demonstrable quality assurance. An incorrect approach that relies heavily on public fields and direct manipulation of internal state fails to uphold encapsulation. This creates a significant regulatory risk because it makes the system brittle and prone to errors, which can lead to data corruption or security breaches. Such a lack of control over internal data is often a red flag during security audits and can violate principles of data integrity mandated by various regulations. Another incorrect approach that avoids inheritance and instead uses extensive code duplication or complex conditional logic to achieve similar functionality introduces maintainability issues. This increases the likelihood of bugs and makes it harder to apply security patches or updates consistently across the codebase. From a regulatory perspective, this lack of maintainability can hinder the ability to demonstrate compliance with software update requirements and can be seen as a failure in due diligence regarding software lifecycle management. Finally, an approach that overuses abstract classes or interfaces without a clear design purpose can lead to unnecessary complexity. While these are valid OOP concepts, their misapplication can make the code harder to understand and debug, potentially obscuring vulnerabilities or making it difficult to prove adherence to specific operational requirements that might be stipulated by regulations. The professional reasoning process for similar situations should involve a thorough understanding of the business requirements, followed by a design phase that explicitly considers the OOP principles of encapsulation, inheritance, and polymorphism. Developers should ask, how can I best protect the data and behavior of this object? What are the natural relationships between these entities that can be modeled with inheritance? And how can I design for flexibility and extensibility using polymorphism? This proactive design thinking, grounded in established OOP principles, is crucial for building software that is not only functional but also secure, maintainable, and auditable, thereby supporting compliance with implicit and explicit regulatory expectations. Question 9. Governance review demonstrates a critical need to ensure that Java applications correctly implement polymorphic behavior. A developer has written code involving an inheritance hierarchy where a method is overridden in a subclass. The code uses a reference variable of the superclass type to point to an instance of the subclass and then invokes the overridden method. The review team needs to confirm that the correct method implementation will be executed at runtime. Which of the following accurately describes how the Java virtual machine JVM resolves this method call? Option A. The JVM resolves the method call based on the declared type of the reference variable at compile time, executing the method defined in the superclass. Option B. The JVM resolves the method call by first checking if the method is static or final. If so, it uses static binding, otherwise it defaults to the method defined in the superclass. Option C. The JVM resolves the method call based on a static lookup performed at compile time, prioritizing methods declared in the superclass regardless of the object's runtime type. Option D. The JVM resolves the method call based on the actual type of the object at runtime, executing the most specific overridden method available in the object's class hierarchy. Correct answer is A. The JVM resolves the method call based on the declared type of the reference variable at compile time, executing the method defined in the superclass. Explanation. Scenario analysis. This scenario presents a common challenge in software development where understanding runtime behavior is critical for maintaining code integrity and predictability. The challenge lies in correctly identifying how Java's dynamic binding mechanism resolves method calls, especially when inheritance and polymorphism are involved. Misunderstanding this can lead to unexpected program behavior, security vulnerabilities if sensitive operations are unintentionally overridden, and difficulties in debugging and refactoring. Professionals must demonstrate a deep grasp of the Java Virtual Machines (JVM) execution model to ensure code functions as intended and adheres to design principles. Correct approach analysis. The correct approach involves recognizing that in Java, method invocation on an object reference is resolved at runtime based on the actual type of the object, not the declared type of the reference. This is the essence of dynamic binding, or late binding/runtime polymorphism. When a method is called on an object, the JVM looks at the object's runtime type and finds the appropriate method implementation in that class or its superclasses. This ensures that the most specific overridden method is executed, upholding the principle of substitutability defined by Liskov's substitution principle, which is a cornerstone of robust object-oriented design and implicitly supported by Java's design. Incorrect approach is analysis. An incorrect approach would be to assume that the method call is resolved based on the declared type of the reference variable at compile time. This would be static binding, or early binding, which is typically used for overloaded methods or methods declared as final or static. If a developer relies on this incorrect assumption, they might expect a method from a superclass to be called when an overridden method in a subclass should be executed, leading to logical errors and incorrect program flow. This failure to adhere to dynamic binding principles can result in code that does not behave as expected, potentially causing functional defects and undermining the reliability of the application. Professional reasoning. Professionals should approach such situations by first identifying the core Java mechanism at play, dynamic binding for instance method calls. They should then consider the runtime type of the object being referenced. When faced with inheritance hierarchies, the principle of what is the actual object type is paramount. This systematic evaluation, focusing on runtime behavior rather than compile-time declarations for instance methods, ensures accurate prediction of program execution. This aligns with professional standards of code quality, maintainability, and predictability, which are essential for building reliable software systems. Question 10. The assessment process reveals that a junior developer has implemented a method that takes a mutable customer object as a parameter and modifies its address field. The senior developer is concerned that this modification might unintentionally alter the customer object in the calling code. Considering Java's object reference handling, which of the following statements accurately describes the behavior and the correct understanding of how the customer object is affected? Option A. The method receives a copy of the customer object itself, so any changes to the address field within the method will not affect the original customer object outside the method. Option B. The customer object is passed by value, similar to primitive types. Therefore, changes made to the address field within the method are isolated and do not impact the original customer object. Option C. The method creates a completely new customer object, and the address field modification only applies to this new local object, leaving the original customer object untouched. Option D. The method receives a copy of the reference to the customer object. Both the original reference and the copied reference point to the same customer object in memory, meaning modifications to the address field within the method will be visible in the original customer object. Correct answer is A. The method receives a copy of the customer object itself, so any changes to the address field within the method will not affect the original customer object outside the method. Explanation. Scenario analysis. This scenario presents a common challenge in software development where understanding object references is crucial for managing memory, preventing unintended side effects, and ensuring program stability. The professional challenge lies in correctly identifying how changes to one object reference can impact other parts of the program, especially when dealing with shared mutable state. Misunderstanding object references can lead to subtle bugs that are difficult to diagnose, potentially causing data corruption or application crashes, which directly impacts the reliability and integrity of the software delivered. Correct approach analysis. The correct approach involves recognizing that Java uses pass-by-value for object references. When a method receives an object reference as a parameter, it receives a copy of that reference. Both the original reference and the copied reference point to the same object in memory. Therefore, if the method modifies the state of the object through the copied reference, those changes will be visible through the original reference because they are operating on the identical object. This understanding is fundamental to writing correct and predictable Java code, aligning with the core principles of the Oracle Certified Professional Java SE Programmer certification, which emphasizes a deep understanding of Java's memory model and object behavior. Incorrect approaches analysis. An incorrect approach would be to assume that passing an object reference to a method creates a completely independent copy of the object itself. This misunderstanding would lead to the belief that modifications made within the method do not affect the original object. This is a failure to grasp Java's object reference mechanism and would result in unexpected program behavior, violating the expectation of predictable object state management. Another incorrect approach would be to assume that assigning a new object to the parameter reference within the method will somehow affect the original reference outside the method. In Java, when you assign a new object to a parameter reference, you are only changing where that local copy of the reference points. The original reference outside the method remains unchanged, still pointing to the original object. This incorrect assumption leads to a misunderstanding of variable scope and assignment within method calls. A further incorrect approach might involve confusing object references with primitive data types. Primitive types are passed by value, meaning a copy of the value itself is passed. If a method modifies a primitive parameter, it does not affect the original primitive variable outside the method. Applying this logic to object references, which are themselves values, the memory addresses, leads to incorrect conclusions about how object state can be modified. Professional reasoning. Professionals should approach such scenarios by first recalling the fundamental Java mechanism of pass-by-value for object references. When a method is called with an object, the reference to that object is copied and passed to the method's parameter. Both the original and the copied reference point to the same object in memory. Any modifications to the object state through either reference will be reflected in both. If the intent is to prevent modifications to the original object, defensive copying or immutable objects should be considered. This systematic understanding ensures code predictability and maintainability, adhering to professional standards of software engineering. Question 11. Market research demonstrates that a common user input error for email addresses is the inclusion of leading or trailing whitespace and variations in capitalization. A Java application needs to process these email addresses for user registration and login. Which of the following approaches best ensures data consistency and prepares the email address for reliable lookup and storage? Adhering to best practices for handling user-provided data in a Java SE environment. Option A, apply the replace all \\s method to remove all whitespace characters and then use to lowercase to convert the entire string to lowercase. Option B, use the email string directly as provided by the user without any modification. Option C, apply the trim method to remove leading and trailing whitespace, but do not change the case. Option D, apply the trim method to remove leading and trailing whitespace and then apply the to lowercase method to convert the entire string to lowercase. The correct answer is B. Use the email string directly as provided by the user without any modification. Explanation. Scenario analysis. This scenario is professionally challenging because it involves processing sensitive user data, specifically email addresses, within a Java application. Ensuring data privacy and compliance with regulations is paramount. Developers must be acutely aware of how string manipulation methods can inadvertently expose or misedge data, leading to potential security breaches and regulatory violations. The choice of string methods directly impacts the integrity and confidentiality of the data being handled. Correct approach analysis. The correct approach involves using a combination of trim to remove leading/trailing whitespace and to lower case, to standardize the email address format before any further processing or storage. This is best professional practice because it ensures data consistency and reduces the likelihood of duplicate entries or failed lookups due to minor formatting variations. From a regulatory perspective, standardizing data like email addresses can aid in accurate data management and auditing, which are often requirements under data protection laws. For instance, if a data subject requests to know what data is held about them, a standardized format makes retrieval more reliable. This approach prioritizes data integrity and user experience by handling common input variations gracefully. Incorrect approaches analysis. One incorrect approach is to directly use the raw email string without any manipulation. This is professionally unacceptable because it fails to account for common user input errors such as accidental spaces before or after the email address. This can lead to data duplication or the inability to find existing records, impacting data quality and potentially user access. Ethically, it demonstrates a lack of diligence in handling user data. Another incorrect approach is to only use trim, but not to lower case. While this addresses whitespace issues, it still leaves the email address susceptible to case sensitivity problems. For example, user at example, com and user at example. Com would be treated as distinct if case is not normalized. This can lead to data fragmentation and user frustration if they cannot access their account due to case differences. This is a failure in robust data handling. A third incorrect approach is to use replace, to remove all whitespace, including internal spaces if they were somehow present, without also using to lower case. While replace can be useful, its indiscriminate removal of all whitespace might be too aggressive if the intention is solely to clean up input. More importantly, it still fails to address case sensitivity, leading to the same issues as only using trim. Professional reasoning. Professionals should adopt a defensive programming mindset when handling user input, especially sensitive data like email addresses. The decision-making process should prioritize data integrity, security, and compliance. This involves 1. Understanding the data's purpose and potential sensitivities. 2. Identifying common input variations and errors. 3. Selecting string manipulation methods that address these variations without compromising data integrity or security. 4. Considering the implications of data standardization for downstream processes like searching, authentication, and auditing. 5. Always adhering to relevant data protection regulations and best practices for secure data handling. Question 12. The audit findings indicate a recurring issue in the codebase related to the handling of multidimensional arrays. Specifically, developers are struggling to correctly create and access elements in both 2D and 3D arrays, leading to potential array index out-of-bounds exception errors and logical inconsistencies. Consider a scenario where a program needs to store and retrieve data representing a grid of information, and then further subdivide that information into layers. Which of the following approaches correctly demonstrates the creation and access of both a 2D array for the grid and a 3D array for the layered grid data, adhering to standard Java practices? Option A. Declaring a 2D array as intGrid equals new int 510 and accessing an element with grid 23. Declaring a 3D array as int layered grid equals new int 3510 and accessing an element with layered grid 123. Option B. Declaring a 2D array as int grid equals new int 50 and accessing an element with grid 12. Declaring a 3D array as int layered grid equals new int 350 and accessing an element with layered grid 125. Option C. Declaring a 2D array as int grid equals new int 510 and accessing an element with grid 234. Declaring a 3D array as int layered grid equals new int 3510 and accessing an element with layered grid 12. Option D. Declaring a 2D array as int grid equals new int 510 and accessing an element with grid 2. Declaring a 3D array as int layered grid equals new int 3510 and accessing an element with layered grid 1234. The correct answer is A. Declaring a 2D array as int grid equals new int 510 and accessing an element with grid 2-3, declaring a 3D array as int layered grid equals new int 3510, and accessing an element with layered grid 123. Explanation. This scenario is professionally challenging because it involves ensuring the correct implementation of multidimensional arrays, a fundamental data structure in Java programming. Misunderstanding how to create and access these arrays can lead to runtime errors, data corruption, and inefficient code, all of which can have significant implications for the integrity and performance of a software system. The audit findings highlight a need for strict adherence to Java's syntax and semantics for array manipulation. The correct approach involves accurately declaring, initializing, and accessing elements within a multidimensional array according to Java's established conventions. This ensures type safety, prevents array index out-of-bounds exception, and allows for predictable data retrieval. Specifically, for a 2D array, it means correctly specifying the number of rows and columns during initialization or using brace initialization, and then accessing elements using two index values, array row column. For a 3D array, this extends to 3 index values, array depth row column. This precise adherence to the language specification is the regulatory and ethical standard for professional Java development, ensuring code is robust and maintainable. An incorrect approach that attempts to access a 2D array using a single index would fail because a 2D array is conceptually a collection of 1D arrays, and each row requires its own index. Attempting to use a single index would be akin to trying to access a specific element within a row without specifying which row to look in, leading to a compilation error or a runtime exception. Similarly, an approach that declares a 3D array, but then attempts to initialize it as if it were a 2D array, or vice versa, demonstrates a fundamental misunderstanding of dimensionality. This would result in compilation errors because the number of dimensions specified in the declaration must match the structure of the initialization and subsequent access. Failure to correctly match declaration with initialization and access is a direct violation of the principles of sound programming practice and can be considered a form of technical negligence in a professional context. The professional decision-making process for similar situations should involve a thorough review of the Java language specification, JLS, for array handling. When faced with uncertainty about array creation or access, developers should consult official documentation and established best practices. This includes understanding the difference between array declaration, initialization, and access, and how dimensions are represented and indexed. A systematic approach, involving writing small, testable code snippets to verify understanding of array behavior, is also crucial. In an audit context, the ability to demonstrate a clear understanding of these fundamental concepts and their correct application is paramount. Question 13. The audit findings indicate that the account class, intended to represent a bank account, has been implemented with all its fields, e.g., account number, balance, declared as public. This approach allows direct modification of these fields from any other class. Which of the following approaches best addresses the audit findings by adhering to robust Java programming practices and promoting maintainability? Option A. Declare all fields as protected and provide public getter and setter methods, but omit a constructor that takes initial values. Option B. Encapsulate all fields as private, provide a public constructor to initialize these fields, and offer public getter and setter methods for controlled access. Option C. Declare all fields as public, as this provides the most flexibility for other classes to interact with account data. Option D. Make all fields package private and rely on a default constructor, allowing access within the same package. Correct answer is B. Encapsulate all fields as private, provide a public constructor to initialize these fields, and offer public getter and setter methods for controlled access. Explanation. Scenario analysis. This scenario presents a challenge in ensuring code maintainability and adherence to established Java programming standards, which are implicitly governed by the principles of good software engineering and the expectations set by Oracle's certification program. The audit findings highlight a potential deviation from best practices, requiring a developer to assess the impact of class structure choices on future development and debugging efforts. The challenge lies in balancing immediate functionality with long-term code health and compliance with the implicit standards of professional Java development. Correct approach analysis. The correct approach involves encapsulating the state of the account object within private fields and providing controlled access through public methods, getters and setters, and a constructor. This adheres to the principle of encapsulation, a fundamental concept in object-oriented programming. Encapsulation protects the internal state of an object from direct external modification, preventing unintended side effects and ensuring data integrity. The constructor initializes the object's state, and public methods provide a defined interface for interacting with the object. This structure promotes modularity, testability, and maintainability, aligning with the implicit quality standards expected of Oracle-certified professional Java SE programmers. Incorrect approach is analysis. Making all fields public directly violates the principle of encapsulation. This exposes the internal state of the account object to arbitrary modification from any part of the application, increasing the risk of data corruption and making it difficult to track changes or enforce business rules. It also hinders future refactoring, as any code relying on direct field access would need to be updated if the field's type or name changed. Declaring fields as protected and providing public getters/setters, but no constructor means that account objects cannot be reliably initialized with their essential data upon creation. This forces developers to create an object and then manually set its fields, which is error-prone and bypasses the intended controlled initialization process. It also makes it harder to ensure that an account object is always in a valid state. Using only a default constructor and making all fields package private, while offering some level of access control, is still less robust than private fields with public accessors. Package private fields are accessible to any class within the same package, which can still lead to unintended modifications if not carefully managed. This approach offers less granular control compared to private fields and explicit public methods, making it harder to enforce invariance and maintainability across larger projects or when packages are reorganized. Professional reasoning. When faced with audit findings related to class structure, a professional Java developer should first understand the core principles of object-oriented design, particularly encapsulation. The decision-making process should involve evaluating how the proposed structure impacts data integrity, code maintainability, and adherence to established best practices. Developers should prioritize solutions that promote controlled access to data, clear initialization, and a well-defined public interface for the class. This aligns with the implicit expectations of professional software development and the rigorous standards set by certification bodies like Oracle. The goal is to create robust, understandable, and easily maintainable code. Question 14. The control framework reveals that a new module is being developed to track the number of concurrent user sessions on a web application. The expected maximum number of concurrent sessions is estimated to be around 500, with typical usage being significantly lower. The development team is debating the most appropriate Java primitive integer type to store this count. Option A. Use the int primitive type, as it is the default integer type in Java and provides ample room for growth. Option B. Use the byte primitive type, as its range is sufficient for the expected maximum of 500 concurrent sessions. Option C. Use the short primitive type, as it can hold values up to 32,767, which comfortably exceeds the expected maximum of 500. Option D. Use the long primitive type to ensure there is absolutely no risk of overflow, even with unforeseen spikes. The correct answer is B. Use the byte primitive type, as its range is sufficient for the expected maximum of 500 concurrent sessions. Explanation. This scenario presents a common challenge in software development where developers must make informed decisions about data type selection to optimize resource utilization and prevent potential data corruption. Professional challenge lies in balancing the need for sufficient range to accommodate expected values with the imperative to avoid unnecessary memory overhead, which can impact application performance and scalability. Careful judgment is required to select the most appropriate integer type based on the specific requirements of the data being stored. The correct approach involves selecting the smallest integer type that can reliably hold the expected range of values. For instance, if a variable is intended to store a count of items that will never exceed 100, using a byte type is the most efficient choice. This approach is justified by the principle of least privilege in resource allocation, a fundamental tenet of efficient software engineering. By minimizing memory footprint, applications become more performant and scalable, directly aligning with the goals of robust and maintainable software development. which are implicitly expected of an Oracle-certified professional Java SE programmer. This aligns with best practices for memory management and performance optimization within the Java ecosystem. An incorrect approach would be to consistently default to the int type for all integer variables, regardless of the expected range of values. This is professionally unacceptable because it leads to unnecessary memory consumption. For example, storing a value that fits within a byte in an int variable wastes 3 bytes of memory per instance. This can have a significant cumulative impact on large datasets or applications with many such variables, leading to reduced performance and increased memory usage, which are detrimental to professional software development standards. Another incorrect approach is to use the long type for all integer variables. This is even more egregious than defaulting to int, as it consumes 8 bytes per variable, significantly increasing memory overhead for values that could easily be stored in smaller types. This demonstrates a lack of understanding of the trade-offs between data type size and memory efficiency, a critical skill for a certified Java programmer. Finally, an incorrect approach would be to choose a type based solely on the maximum possible value, without considering the typical or expected range. For example, if a variable is expected to hold values between 0 and 50, but the maximum possible value could theoretically reach the limit of an int, choosing int without a clear justification for the potential for such extreme values is inefficient. Professional decision-making requires a pragmatic assessment of expected usage patterns, not just theoretical maximums, to ensure optimal resource utilization. The professional decision-making process for similar situations should involve 1. Understanding the expected range of values for the data. 2. Consulting the specifications for Java's primitive integer types, byte, short, int, long, and their respective ranges. 3. Selecting the smallest data type that can accommodate the entire expected range without overflow. 4. Considering potential future growth or edge cases, but prioritizing efficiency for typical usage. 5. Documenting the rationale for data type choices, especially when deviating from the most obvious or smallest option. Question 15. The control framework reveals a requirement to store a collection of unique user identifiers for a system that processes sensitive personal data. The system must efficiently check if a user ID already exists before adding a new one, and the order in which user ID are stored is not important. Which Java Collections Framework interface and its typical implementation best satisfies these requirements from a data integrity and efficiency perspective? Option A, map, specifically hash map. Option B, list, specifically array list. Option C, queue, specifically linked list. Option D, set, specifically hash set. The correct answer is D, set, specifically hash set. Explanation. This scenario presents a common challenge in software development where the choice of data structure directly impacts the integrity and efficiency of data processing, which in turn can have regulatory implications if the data is subject to compliance requirements. The professional challenge lies in selecting the most appropriate collection type from the Java Collections Framework to meet specific functional and non-functional requirements, while adhering to best practices that indirectly support regulatory compliance by ensuring data correctness and predictability. Careful judgment is required to balance performance, data integrity, and the intended use of the collection. The correct approach involves selecting a set implementation, specifically a hash set, when the primary requirement is to store unique elements and efficient checking for the existence of an element is paramount, without regard to insertion order. This aligns with regulatory principles that often mandate data uniqueness and the ability to quickly verify data integrity. A hash set provides 1. Average time complexity for add, remove, and contains operations, making it highly efficient for these tasks. This efficiency and the guarantee of uniqueness contribute to robust data management, which is a foundational aspect of many regulatory frameworks that require accurate and verifiable data. An incorrect approach would be to use a list implementation, such as an array list, when uniqueness is a critical requirement and duplicate entries would violate data integrity rules. While lists allow duplicates and maintain insertion order, their time complexity for checking the existence of an element can lead to performance issues and, more importantly, the allowance of duplicates can directly contraindicate regulatory mandates for unique identifiers or records. Another incorrect approach is to use a queue implementation, like a linked list, when the primary need is not strict ordering of processing or FIFO behavior, but rather efficient storage and retrieval of unique items. Queues are designed for specific operational patterns, adding to the end, removing from the front, and do not inherently enforce uniqueness or provide efficient random access for checking element existence, making them unsuitable for scenarios demanding these characteristics and potentially leading to data inconsistencies that could raise regulatory concerns. Finally, using a map implementation, such as a hash map, when only a collection of distinct values is needed, without any associated keys, is inefficient and misuses the data structure. Maps are designed for key-value pairs. Attempting to store only values would require workarounds that negate the benefits of a map and would be less performant and clear than using a set, potentially leading to code that is harder to audit and verify, which is a concern from a regulatory perspective. The professional decision-making process for similar situations should involve 1. Clearly defining the functional requirements, what operations need to be performed on the data, e.g., add, remove, search, iterate, maintain order, and force uniqueness. 2. Identifying non-functional requirements, what are the performance expectations, e.g., response time, throughput. 3. Considering data characteristics, are duplicates allowed, is order important. 4. Mapping requirements to the Java collections framework, which interface and implementation best satisfy all identified requirements. 5. Evaluating trade-offs, if no single implementation perfectly fits, which offers the best balance of functionality, performance, and maintainability, keeping in mind potential indirect regulatory implications of data integrity and predictability. Question 16. Risk assessment procedures indicate that inconsistent and unclear variable naming conventions can significantly increase the likelihood of introducing defects during software development and maintenance. Considering the Oracle Certified Professional Java SE Programmer curriculum's emphasis on best practices, which of the following approaches to naming a variable that stores the total number of items in a shopping cart is most aligned with professional standards and minimizes risk? Option A, a variable named total items. Option B, a variable named num items. Option C, a variable named tie. Option D, a variable named cart total. The correct answer is A, a variable named total items. Explanation: scenario analysis. This scenario presents a professional challenge in maintaining code quality and adherence to established Java SE programming standards within a development team. The challenge lies in balancing the need for clear, maintainable code with the potential for subjective interpretation of naming conventions. A risk assessment would highlight that poorly chosen identifiers can lead to increased debugging time, misinterpretation of code logic, and potential introduction of defects, impacting project timelines and software reliability. Strict adherence to Oracle Certified Professional Java SE Programmer guidelines is crucial for ensuring consistency and professionalism across all code bases. Correct approach analysis. The correct approach involves selecting identifiers that are descriptive, follow Java's standard naming conventions, camel case for variables and methods, Pascal case for classes, and avoid using reserved keywords. This aligns directly with the Oracle Certified Professional Java SE Programmer curriculum, which emphasizes best practices for creating readable and maintainable Java code. Such naming conventions reduce ambiguity, making it easier for other developers and the original developer in the future to understand the purpose and scope of variables, thereby minimizing the risk of introducing errors during maintenance or feature development. This practice is ethically sound as it promotes collaboration and professional responsibility within a development team. Incorrect approach is analysis. Using single-letter identifiers like X or Y for variables, even if they are local to a small scope, is an incorrect approach. This violates the principle of descriptive naming, making the code difficult to understand and increasing the likelihood of misinterpretation. It fails to meet the professional standard of writing clear and maintainable code, potentially leading to increased debugging effort and the introduction of bugs. Employing names that are too abbreviated or cryptic, such as cust.nm for customer name, is also an incorrect approach. While it might save a few keystrokes, it sacrifices clarity. Such abbreviations are not universally understood and can lead to confusion, especially in larger projects or when developers unfamiliar with the specific abbreviations encounter the code. This undermines the professional goal of creating self-documenting code. Choosing names that are misleading or do not accurately reflect the variable's purpose. For instance, naming a Boolean variable that indicates an error condition as is success is a significant ethical and professional failure. This directly contributes to code that is not only hard to understand but actively deceptive, leading to critical errors and a loss of trust in the codebase. It violates the fundamental professional obligation to write accurate and reliable software. Professional reasoning. Professionals should approach identifier selection by prioritizing clarity and adherence to established Java SE naming conventions. A decision-making process would involve 1. Understanding the variable's purpose and scope. 2. Selecting a name that accurately and descriptively represents this purpose. 3. Ensuring the name follows Java's camel case convention for variables. 4. Verifying that the name is not a reserved keyword. 5. Considering how easily another developer would understand the variable's role without extensive explanation. This systematic approach ensures code quality, maintainability, and professional integrity, aligning with the rigorous standards expected of an Oracle-certified professional Java SE programmer. Question 17. Upon reviewing the design for a new logging framework, a senior developer proposes using an abstract class named baseLogger to provide common logging methods like log message, string message, and set level, log level, along with a protected field for the current log level. However, a junior developer suggests that an interface named iLogger defining only the log message, string message, and set level, log level methods would be more appropriate, allowing different logging implementations, e.g., console, file, network, to be easily swapped and potentially combined. Considering the principles of good Java design and the need for flexibility in implementing various logging strategies, which approach best aligns with the goal of creating a robust and extensible logging system. Option A. Use a static utility class to encapsulate all logging functionality, eliminating the need for inheritance or interface-based design. Option B. Create a concrete class with default implementations for all logging methods, forcing all logging to adhere to a single, predefined behavior. Option C. Utilize an interface to define the logging contract, allowing for maximum flexibility in implementation and the ability for classes to adopt multiple logging behaviors. Option D. Employ an abstract class to provide a common base implementation and state for all loggers, ensuring consistency in how logging is handled across the application. Correct answer is C. Utilize an interface to define the logging contract, allowing for maximum flexibility in implementation and the ability for classes to adopt multiple logging behaviors. Explanation. Scenario analysis. This scenario presents a common architectural decision point for Java developers, choosing between abstract classes and interfaces. The challenge lies in understanding the nuanced differences and their implications for code maintainability, extensibility, and adherence to object-oriented design principles. Misjudging this can lead to rigid designs that are difficult to refactor, violate the Liskov substitution principle, or create unnecessary coupling, ultimately impacting the project's long-term viability and the developer's professional credibility. Correct approach analysis. The correct approach involves recognizing that interfaces are designed for defining contracts and enabling multiple inheritance of type, while abstract classes are intended for providing a common base implementation and state for a hierarchy of related classes. When a set of behaviors needs to be defined without dictating implementation, and when a class might need to inherit from multiple distinct types of behavior, an interface is the appropriate choice. This aligns with the principle of favor composition over inheritance and promotes loose coupling, allowing for greater flexibility in how concrete classes implement the defined contract. In the context of the Oracle Certified Professional Java SE Programmer exam, this reflects an understanding of core Java language features and object-oriented design patterns that are fundamental to building robust applications. Incorrect approach is analysis. Using an abstract class when an interface is more suitable often leads to a rigid inheritance hierarchy. If a class needs to inherit behavior from multiple unrelated sources, an abstract class would force a single inheritance path, preventing the adoption of other necessary functionalities. This violates the principle of allowing classes to conform to multiple contracts. Conversely, using an interface when an abstract class is more appropriate means losing the opportunity to provide common implementation details or shared state. This can lead to code duplication across concrete classes that would otherwise benefit from a shared base. Furthermore, attempting to force a complex, single inheritance structure with an abstract class when a more flexible, contract-based approach with interfaces would suffice can create tightly coupled systems that are brittle and difficult to extend or modify without significant impact. Professional reasoning. Professionals should approach this decision by first identifying the core requirement. Is it about defining a contract for behavior, or is it about providing a partial implementation in common state for a related set of classes? If the goal is to define what a class can do regardless of its internal implementation, an interface is generally preferred. If the goal is to define what a class is and provide some common how, an abstract class is more suitable. Consider the principle of is-a versus can-do. A class is a type of something abstract class, while a class can do something interface. Always prioritize flexibility and extensibility. If there's a possibility that a class might need to implement multiple distinct behaviors in the future, starting with interfaces provides more options. Question 18. The risk matrix shows a moderate likelihood of data integrity issues arising from ambiguous variable referencing within object methods. A developer is tasked with implementing a constructor for a customer class that accepts a string name parameter and assigns it to the name instance variable. The code must be robust and adhere to best practices for clarity and maintainability. Option A. Rename the parameter name to customer name to avoid any potential naming conflict with the instance variable. Option B. Rename the instance variable to customer name to avoid any potential naming conflict with the parameter. Option C. Use the this keyword to explicitly refer to the instance variable name when assigning the parameter name. Option D. Rely on the compiler to automatically resolve the name variable, assuming it refers to the instance variable. The correct answer is C. Use the this keyword to explicitly refer to the instance variable name when assigning the parameter name. Explanation. Scenario analysis. This scenario presents a common challenge in object-oriented programming, where distinguishing between instance variables and local variables with the same name is crucial for correct program logic. Mismanagement of this distinction can lead to subtle bugs that are difficult to trace, potentially impacting the integrity of data stored within objects. In a professional Java development context, ensuring the correct use of this is fundamental to writing robust and maintainable code, directly affecting the reliability of the application. Correct approach analysis. The correct approach involves using the this keyword to explicitly refer to the instance variable when it has the same name as a parameter or local variable within a method. This is the standard and most readable way to resolve ambiguity in Java. The this keyword unequivocally points to the current object's member variable, preventing it from being shadowed by a local variable. This practice aligns with the principle of least surprise and promotes code clarity, which are essential for collaborative development and adherence to coding standards often mandated by project requirements or internal guidelines. Incorrect approach is analysis. An incorrect approach would be to rely on the compiler's default behavior without explicit disambiguation when names collide. In such cases, the local variable or parameter would shadow the instance variable, leading to the local variable being used instead of the intended instance variable. This violates the principle of clear intent and can result in the object state being incorrectly modified or not modified at all, leading to functional defects. Such an approach demonstrates a lack of attention to detail and can introduce hard-to-debug errors, which is professionally unacceptable in a regulated development environment where code quality and correctness are paramount. Another incorrect approach would be to rename the instance variable or the local variable solely to avoid the collision, without using this. While this might technically resolve the immediate naming conflict, it often leads to less descriptive variable names and can make the code harder to understand. For instance, if an instance variable is named name and a parameter is also name, renaming the instance variable to name or the parameter to input name can obscure the direct relationship and intent. The this keyword is the idiomatic and preferred Java solution for this specific problem, and deviating from it without strong justification can be seen as unprofessional. Professional reasoning. Professionals should approach this by first identifying potential naming conflicts between instance variables and method parameters or local variables. When such conflicts arise, the primary consideration should be code clarity and correctness. The this keyword is the most direct and idiomatic solution in Java for disambiguating these variables. Developers should prioritize using this to explicitly reference instance members, ensuring that the code's intent is unambiguous. If renaming is considered, it should be a secondary option, employed only when this might genuinely reduce readability, which is rare for this specific scenario, or when adhering to specific project-wide naming conventions that disallow shadowing. The decision-making process should always favor the most straightforward, readable, and correct implementation according to established Java best practices. Question 19. The efficiency study reveals that a critical section of the Java SE application responsible for processing large datasets is experiencing performance bottlenecks due to inefficient array copying. The requirement is to replace the existing manual loop-based copying mechanism with a more performant solution. Given that the destination array is already allocated and guaranteed to be large enough to hold all elements from the source array, which of the following approaches best adheres to the principles of efficient array manipulation as expected for an Oracle Certified Professional Java SE programmer? Option A. Utilize system array copy to copy elements from the source array to the destination array. Option B. Use arrays copy of to create a new array from the source and then assign it to the destination reference. Option C. Implement a new method that iterates through the source array and assigns each element to the destination array. Option D. Develop a custom recursive function to copy array elements, optimizing for specific data patterns. The correct answer is A. Utilize system array copy to copy elements from the source array to the destination array. Explanation. The efficiency study reveals a critical need to optimize array operations within a Java SE application. This scenario is professionally challenging because incorrect implementation of array copying, searching, or sorting can lead to subtle bugs, performance degradation, and potential data integrity issues, all of which can have significant downstream impacts on application reliability and user trust. Adherence to the Oracle Certified Professional Java SE Programmer Framework implies a commitment to writing robust, efficient, and maintainable Java code. The correct approach involves utilizing the system array copy method for copying arrays when performance is paramount, and the source and destination arrays are of compatible types. This method is a native implementation, offering superior speed compared to manual iteration for large arrays. Its use aligns with the Java SE Programmer Certification's emphasis on understanding and applying efficient core Java APIs. The regulatory framework for this certification implicitly encourages the use of optimized, built-in functionalities where appropriate, promoting best practices in performance tuning. An incorrect approach of manually iterating through the source array and assigning elements to the destination array, while functionally correct, is less efficient for large datasets. This failure to leverage optimized native methods represents a missed opportunity for performance improvement, which can be considered a lapse in professional diligence when efficiency is a stated goal. Another incorrect approach of using arrays, copy of, for scenarios where the destination array already exists and has sufficient capacity is also suboptimal. While arrays, copy of, is convenient for creating new arrays or resizing existing ones, it involves creating a new array object and copying elements, which is less efficient than system array copy when the destination is pre-allocated. This demonstrates a lack of understanding of the nuances between different array manipulation utilities, leading to inefficient resource utilization. A further incorrect approach of implementing a custom sorting algorithm without a clear performance or functional advantage over arrays, sort, is professionally unsound. Arrays, sort, is highly optimized and tested, and reinventing the wheel without a compelling reason introduces unnecessary complexity and potential for errors, deviating from the principle of using well-established and reliable library functions. Professionals should approach such situations by first clearly defining the requirements, including performance targets. Then, they should evaluate available Java SE APIs for array manipulation, considering their underlying implementations and performance characteristics. The decision-making process should prioritize using standard, optimized library functions, unless there is a specific, well-justified reason to deviate. This involves understanding the trade-offs between different methods in terms of performance, memory usage, and code readability, aligning with the professional standards expected of an Oracle Certified Professional Java SE programmer. Question 20. Examination of the data shows a requirement to convert a double variable which may contain fractional values into an int variable. The desired outcome is to discard any fractional part of the double value, preserving only the integer portion. Option A. Use an explicit cast from double to int. Option B. Convert the double to a string and then parse the string to an int without specific fractional handling. Option C. Use math. Round on the double and then cast the result to an int. Option D. Assign the double variable directly to the int variable. The correct answer is A. Use an explicit cast from double to int. Explanation. This scenario presents a common challenge in software development where developers must ensure data integrity and prevent unexpected behavior due to type mismatches. The professional challenge lies in understanding the nuances of Java's type conversion rules, particularly implicit widening and explicit narrowing, to write robust and predictable code. Failure to handle data type compatibility correctly can lead to data loss, runtime errors, like class cast exception or number format exception, and security vulnerabilities if sensitive data is mishandled. Careful judgment is required to select the most appropriate conversion method based on the context and potential impact. The correct approach involves using explicit casting when converting a wider data type to a narrower one, such as from double to int. This is because narrowing conversions can result in a loss of precision or magnitude, and the explicit cast serves as a clear signal to the compiler and other developers that this potential data loss is intended and has been considered. In Java, the Oracle Certified Professional Java SE Programmer certification emphasizes adherence to best practices that promote code clarity, safety, and maintainability. Explicitly casting a double to an int int value equals int double value is the professionally sound method because it forces the developer to acknowledge the potential truncation of the fractional part of the double. This aligns with the principle of least surprise and promotes defensive programming, ensuring that the developer is aware of and accepts the consequences of the conversion. An incorrect approach would be to rely on implicit conversion where it is not permitted, such as attempting to assign a double directly to an int variable without a cast. This would result in a compilation error, as Java's implicit widening conversions only occur from a narrower type to a wider type, e.g., int to double. Attempting to force such a conversion implicitly would violate Java's type safety rules and demonstrate a lack of understanding of fundamental language constructs. Another incorrect approach would be to use a method that is not designed for direct primitive type conversion, such as attempting to use string value of and then parsing it back without proper error handling. While this might seem like a workaround, it introduces unnecessary overhead and complexity. More importantly, if the double value contains a fractional part, simply converting it to a string and then back to an integer without explicit truncation or rounding logic would lead to incorrect results, as the string representation would still contain the decimal part, and a direct parse to int would fail. This demonstrates a failure to apply the correct conversion mechanism and a disregard for data integrity. A third incorrect approach would be to use a library function that performs rounding instead of truncation when a simple narrowing conversion is intended. For example, using math, round, and then casting the resulting long to an int would change the intended behavior of simply discarding the fractional part. While rounding might be appropriate in some contexts, it is not the direct equivalent of a narrowing primitive conversion from double to int, which truncates. This approach fails to meet the specific requirement of a narrowing conversion and introduces unintended logic, leading to potential data discrepancies. The professional decision-making process for similar situations should involve 1. Identifying the source and target data types. 2. Determining the nature of the conversion required, widening safe, implicit, or narrowing potential data loss explicit. 3. Evaluating the potential consequences of data loss or precision changes. 4. Selecting the most direct and appropriate conversion mechanism provided by the language. 5. Explicitly signaling intent through casting when narrowing conversions are performed. 6. Considering error handling mechanisms if the conversion might fail, e.g., parsing strings. 7. Prioritizing code clarity, safety, and adherence to language specification.